Chemical Kinetics Part 7, Integrated Rate Law for Zero-Order Reactions. Before we talk about any specific order of reaction, let's just make the point that differential rate laws relate rate to concentration. And what we're going to do here is come up with some integrated rate laws so that we can relate concentration to time. Now this is a sheet with all of the important equations that you would need for chemical kinetics. So if you can't do the calculus, that's fine. You don't really ever have to derive the integrated rate law from the differential rate law, but I do want to show you how that works. And in this video, we're going to take a look at that for zero-order reactions. So we're going to take this differential rate law for zero-order reactions and turn it into this integrated rate law. And then we're going to take a look at what that graph tells us. So for zero-order reactions, we start the integrated rate law, and this is for a single reactant A forming products. We start with the differential rate law that says rate is equal to the rate constant K. And the rate is also equal to a negative of the slope of a concentration versus time graph, or a negative of the derivative of concentration versus time. So we're going to take that negative of the derivative of concentration over time and make it equal to K, the rate constant. Rearrange it so we get D, concentration of A, is equal to negative K dt. We're going to integrate it from a lower limit of 0 to an upper limit of T for both sides of the equation. So integration from 0 to T of dA and integration from 0 to T of negative K dt. Now this right hand side simplifies out, the K factors out, and we get the negative K factors out, we get negative K times the integral from 0 to T dt. The left hand side of the equation, well, what is an integral from 0 to T of dA? It's A at time T minus concentration of A at time 0. Negative K is already factored out. The integration of 0 to T dt is T minus 0. Well, negative K times 0 is just 0, so the right-hand side of the equation becomes negative KT. We get this. Rearrange it so we have the concentration of A at time T is equal to a negative of the rate constant K times time plus the concentration of A at time 0. Now notice that this equation in the box takes on the slope-intercept form of a straight line equation, where the concentration of A at time t is y, negative K is m, or the slope of the line, t is x, that's the x-axis variable, and the concentration of A at time 0 is the b value, which is the y-intercept in the slope-intercept equation. Well, that means that if we graph out concentration at any time t on the y-axis versus time t on the x-axis, that we'll get a straight line, because this is a straight line slope-intercept form equation. The slope of that line will be negative K, and the y-intercept for that line will be the concentration of A at time 0. And here we can see that the integrated rate law relates concentration to time graphically. We're going to take a look at how that works for first and second order reactions in separate videos.